Okay, this is our second lecture, and what I want to do is continue. The first lecture I gave a sort of an introduction, and we started with Lagrangian mechanics. It's a part of the whole business of analytical mechanics, and after we do Lagrangian mechanics, I want to do Hamiltonian mechanics. That will take us the most part of our time discussing analytical mechanics. Lagrangian mechanics is at the basis of it all, but there's a little bit less to say. All right, the powerful methods are all the Hamiltonian methods. But I'm convinced you won't understand Hamiltonian methods if you don't have the Lagrangian background. That's the most intuitive, and that's just going to put the foundation of what we want to do interpretation-wise when we do economic engineering. So last time we showed how if we take the law of demand, which I wrote down here, we can get there by doing this thing we call a cost-benefit analysis. And a cost-benefit analysis is our economic engineering term for what's called a Lagrangian analysis of the system. So you take this Lagrangian, which is a running cost, you look over your activity, your course of action, you integrate it out over it, you parameterize that with time, you find out what your period costs are, and you try to minimize that. And that's the idea behind it. And you can figure out that when you do that, that's equivalent to this set of equations involving the price and the desires or the wants, okay? And this equation we recognize as the equation of demand for commodities, but it's a little bit more than that. The law of demand is valid for one commodity at a time. So it's called partial equilibrium. Now, if they are independent, we can add some, and then we can add substitution effects, and maybe we can do some other things. But every time we have to add something to it and see whether it still works. The same in engineering. When we start off with Newton's laws, it just works for one dimension at a time, so we can add 3 dimensions. We imagine holding the other ones fixed. But then when we run out of that idea, we can look at rigid bodies and look at the rotation, and we'll have to develop separately ideas of the moment of inertia, etc. Right? Now, what this thing does, it just solves everything at once. It just says, look, in general, if you can set this thing up like that, this will be your equation of motion. Or this is how your prices will behave. So the prices will only change if there's something called an economic force, which is what we've been calling a desire or a want. All right, and they have to go this way. But this is a complicated equation because these can be vectors. This can be a vector. It can be something very, very complicated. These can depend on anything at all. It's just not the usual law of demand. And that's why I've called it that this result, that a cost-benefit analysis leads to something that economists may call a price system. So you start with your costs and your benefits, and then it allows you to assign prices to the items that you're looking at, all right? Whether they're commodities or whether it's financial capital, real capital, whatever you can think of, all right? So this is called a price system. And for us, for economists, often a price system is not something dynamic. There won't be this dot here that implies a time derivative. For us, we have a dynamic price system. So we can control how the prices move by to get a handle when we get a handle on the forces here, the economic forces, the desires. All right? So with that general result in place and those general pieces of terminology, what I want to do is discuss how this applies to two economic, where's the clicker? Otherwise, I'll use the keyboard here. Huh? Oh, there it is. Huh? Where, at the obvious place where it's supposed to be. So what I want to do is apply it to two different fields of economics. And the first is the theory of the firm. And the second one is consumer theory. So unlike what we're going to do, economists treat individuals, which they sometimes call consumers, which they usually call consumers, I mean, not sometimes, as being separate in principle and also in more than just principle from companies or firms, businesses. So the demand side of things is just treated with a very different theory than the supply side of things. Although in the theory of demand, you would think they're all symmetrical, in the general economic theories, this is not the case. So firms, they focus on profit maximization or cost minimization, things like that. And individuals, they don't do profit maximization. And profit is not something an individual has. You know, it's more something associated with the business. And instead, they will do utility maximization. All right? So it's quite different approaches, and we just have one approach. So what I want to do here is, and we also had this challenge with the theory of demand. Remember, we had an upward sloping line and a downward sloping line, and we do have to do some kind of tricks with minus signs to get these things into vector quantities so we could get one theory which is required when you do Newtonian mechanics. And when you do analytical mechanics, also you don't have two theories for depending on whether the particle is moving to the right or the particle is moving to the left or something like that. You just have one theory, all right? So what I want to do in the beginning of this lecture is show you how these two theories might fit into the single kind of cost-benefit theory that we've put up here, all right? So let's start with this theory of the firm. So we just have our regular thing. We have this action in mechanics that we call the period cost, and this Lagrangian, which we call the running cost. Okay. Now, in the theory and economics, they don't really assign any meaning to this usually. I haven't seen it. If somebody has seen it, I'd like to see a hand or something. But this thing they do, and they call it a cost function usually. So this is not a bad name because the Lagrangian is indeed a function. It's a function of position and velocity. Now this thing here, the action, which is also a cost, but this is a cost measured in dollars over the period, is not a function, right? It's a function null. It's dependent on the path. So you will see something like this. These cost functions, do they look anywhere like what we have, a difference of kinetic energy and potential energy? Most of the time, no, not at all. They look quite simple for our taste. Instead of looking at a half and v squared, they'll do something like multiply a p times a v, where this is a constant, right? So this is not a function of v or anything, right? They'll just do that the total costs are proportional to v, right? So they'll say this is proportional to the quantity, okay? This could be the output. This is often the output. And the prices are just given. It's just some number. So if it's proportional, they say, well, this is the constant of proportionality. It's just the price, okay? Almost always. Now, first, that won't do, of course, because if price is going to be anywhere close to momentum, then only being able to model particles with constant momentum is not very interesting at all. I mean, maybe in statics, but not in dynamics, okay? So that will be a first difference. Now, it's not that they don't do any effort afterwards. So they'll say, all right, okay, the prices are given, but nevertheless, this output can change because they have these inputs and they cost money. And what if the prices of the inputs go up? Then how many output can you produce? And all kinds of stuff like that. But that's not really saying the same as saying the price is just changing because of forces acting on it, okay? You still haven't made that translation step. And if you go through it, you'll see that you're better off throwing a bunch of transformers in there or things like that to look at how their production function works. It's a very complicated things. And so what they try to do is they model these whole firms with these ideas of production functions and other things that are going to determine these price systems. We will never be able to catch this in a Lagrangian where you just have an I element and a C element. This is very complicated things. We'll be able to do it with a big, a very big circuit, probably. So the starting point for us is actually quite a very simple firm. It's just a firm that has some supply here. It's the I element, and has some storage, capacity. That's it. It has an inventory, and it's selling things. It's not even, it's got a damper. It's not even making any money, really. It's just storing stuff and selling it, right? So it's quite a simple firm. And we'll be building on this, but this is our basis, and this is our connection with Lagrangian mechanics, okay? Now, the Lagrangian is the difference between the kinetic co-energy and the potential energy. So T star and V. Now, kinetic co-energy we've been calling the cost. And remember, we have this nice little supply-demand graph, and Marshall tells us that if you do this, this is the surplus, and this is the cost or the expenses. And that's what we've been calling it. Now, the word you'll see in most of this type of work is something called a variable cost, as opposed to a fixed cost. I want to treat the fixed cost a little bit later, how you deal with that. And why is it a variable cost? Well, as you can see, this cost here will depend on the output, right? So V is usually the output. So you're a producer, and as you produce more, it's going to cost you more money because you're using, I don't know, it's like you're using more of your equipment, and you don't have that many resources. So the cost here is dependent on the products itself. So it varies with the product, with the output. And that's why it's called a variable cost. So you can think of it that way. Then remember, the next step we did was define the canonical momentum as the partial derivative of the Lagrangian, right? So you look at the change in your running cost as you increase your output, right? The amount you sell. In a very intuitive way, that is the price, right? So this is our definition of price. So our definition of price really is this thing that price is the marginal cost. When you take these partial derivatives, or maybe even full derivatives sometimes, instead of saying the differential, economists will use the word marginal. Right? So the marginal cost is the increase in the cost when you increase the output with a small amount at a particular point. Huh? So this is a sort of a definition of price. Remember, here prices came out of nowhere, and here we're defining. Now the Lagrangian, of course, comes out of nowhere. It's still something comes out of nowhere. But at least we can, when we have a Lagrangian, we can define this price as that derivative. Now, there's a name for this equation in economics, and it's called Shepard's lemma. Now, for those of you who are in the know about this theory, Shepard's lemma actually doesn't say this literally. It says V is equal to this. Now, this won't do for us because our costs are not going to be a function of the price. So you would have to, like, if you have the Lagrangian as a function of the output, what you will have to do is think of the output as a function of the price and then take the partial derivative with the price, right? Now, if you do that, then you can plug in m times v for this, right? And then you can take the m out, huh? And then if you bring the m to the other side, if you multiply by m both sides, then you get p. And this is the form we wanted in. Huh? So, although it's called Shepard's lemma, it's a famous result. I don't know for what they managed to derive it, the envelope theorem. They do all kinds of tricks. Envelope theorem, right?
Yeah, so that basically.
Yes.
Realization.
Yes.
What they don't do is that they don't see prices.
Right.
So that's the essential difference with processes.
Yeah, so price becomes a state only in Hamiltonian mechanics, actually. So this is Lagrangian, but I think the envelope theorem is really interesting because if you look at the Lagrangian, you know, it's half mv squared, so it's some kind of convex function like that. It probably goes to 0, right? So here's v, here's your Lagrangian, right? I mean, I just plotted a half mv squared. Then what is the price? Well, it's the derivative, right? And it's the slope of this derivative. And then what you can do is you look at the price, so you can look at all these derivatives and construct from them the function, right? Can you imagine that? So if you don't have the function, but you have the derivative here, you have the derivative here, you have the derivative there, right? Then you know that you can just construct a function from that. So what you do is you envelope the function with its derivative. And they call that the envelope theorem. We will see that this thing is just a consequence of something we will call the Legendre transform. All right, and I want to do that next lecture. But what you kind of have to see here is our approach is a little different. You see, we don't have all these derivatives. All we have is the function itself. That's the Lagrangian, right? Huh? And if you have that function, you can find, so it's like the inverse of the envelope theorem in a sense. You can find the derivative, right? And this, the slope you define to be, and this shows you how the price is indeed the marginal cost, because if I increase my supply by a little bit, my cost will increase by this little bit, dl, right? And there you are. So thanks, Kuhn, for just telling us exactly where this comes from. But you see, they get Shepard's lemma from another way. They usually assume they have a price, and then they start trying to figure out what these cost functions are. That's okay. You can do it that way, but that's not what you do when you do a Lagrangian analysis. You don't assume you have a price. You only assume you have a cost function. Now, cost is not about a price. Cost is about this item you buy or this item you store, okay? You can only assign a cost to the actual items, all right? Huh? It's going to be the same with utility. Price has no utility, but the items you're buying and the items you're storing, they have utility. So logically, what we do, we start quite differently. We start with the items themselves, then assign this cost function, and then start assigning all these other variables like price and velocity, price and force, price and convenience, okay? Desires. So that's the same it's done in mechanics, you know, because you can say, for instance, oh, there's a force of 5 Newton acting on this particle. Like, how do you know, right? I mean, how do you measure that? Well, I take my force-o-meter. But what does a force meter do? I mean, nobody's ever really seen a force, right? You can't really build a force meter that just goes and does nothing and then somehow measures that force, you know? So what you need to do with a force meter is look at how much that particle is changing its acceleration, its movement, and then you can calculate the force. So whatever meter you can only measure movements, you know? You just have a ruler and you have time. That's all you have, right? When you start doing mechanics. And from that, you have to derive what mass is and this. This is called an operational definition. So you first decide what you can all agree on. Well, that is because I have a meter rod and I can decide how far this is. I have a clock, so I can decide how much of that distance goes per unit of time. But I can't just all agree like this is 5 Newton. You know, that's nonsense. I have to look at a clock or I have to look at my measuring tape. So when I do my Lagrangian analysis, I have to start from position and velocity and maybe acceleration or things like that. Now it appears that position and velocity are enough. That's why this is at the basis, you see. You can't just say, oh, the mass is 1 kilogram. And how do you know? Well, I just looked at it. You know, with our eyes, we can only see distance and we can look at a clock, right? So we can hear the ticks, count the ticks. That's what all you have. All right? So in a sense, this is cleaner, you know, because if you look at an economy, what do you see? You don't see the prices, right? Well, somebody puts a price there, but how do you look at the internal price of somebody? You don't see that. You can only see what he really buys and sells, what changes hands, all right? What he's doing, right? So to make the theory clean, it's sometimes called to make it operational, right? You gotta start from demand and holdings, things they have in stock, all right? Actually, the only way to count what you have in stock is to first look at demand and then sum it out. So even if you keep inventory, you're just going with your finger down and you add up your flow, but that's a minor issue, all right? These are called an operational definition, and it's got an interesting history because in the end of the 19th century, Newton's theory was there and this and that, and people were asking themselves this question, how much of all this stuff is real, you know? Can we understand, you know? Is a force something real, or is it just doesn't exist, or is energy something real, or it doesn't exist? And there was a guy called Ernst Mach, and he got famous for this Mach number, for the speed of sound. And he developed this idea that the definition had to be operational, so that you have to start off with some things that you all agree on, like position and time and things like that, and that everything should be derivable from those things. And it was called an operational method. And then all kinds of people got very excited about that and started saying, well, okay, then we have to clean up a lot of physics because there was a lot of stuff just lying around that nobody had really operationally defined. And one of these guys, Albert Einstein, and he started looking at the wave equation. He says, well, what is this? The speed here, the speed of what a wave goes, how do I measure that? What is it even, you know, huh? And by pushing that definition, he was able to come up with his theory. He was a big admirer of Mach and his idea. He was able to reformulate how you would have to rethink of Lorenz's equations that were just like, Lorenz had made these equations saying how you could resolve everything, but nobody understood where it came from. And he was able to say, no, you have to change your notion of distance and time enough, and then the whole thing will get together, all together, right? So his theories is all about things you can observe, the speed of light, you know, and meter rods and those kind of things, right? So it's been a very fruitful way to move ahead. And economics has not benefited from this type of perspective change, that every definition has to be operational. And in a sense, what we're doing here is enforcing that idea and making clear that prices don't come out of nowhere. No, this is what you start off with is this Lagrangian, and then, you know, which is based on your demand and your stock holdings. And from that, you define your price, okay? So I feel this is the cleaner version of Shepard's limit. I just wrote it down here, but there's a little bit of Yeah, a little different. Then we figured out that the mass is now the second derivative, so of the cost. And this is the inverse of the price elasticity. Now, the mass is a positive number, right? I'm not going to bother to prove that. You can prove that. I guess you can't really prove it, but you can show that if it isn't, it's ridiculous what's going to happen in the world, you know? And but it is important to realize that economists also assume that this mass defined in this way is positive, okay? So that the price elasticity, well, it looks negative, and, well, it looks positive on the supply graph, so we're okay here, right? But then it has to be always positive, and they call it the law of diminishing marginal returns. It's a little confusing because you would like to have a law of increasing cost or something, but they measure it from this way. So this is what they would think of as the return, and then this one is diminishing. So the negative side is diminishing. A little confusing, but the meaning is this, okay? It's an important law of economics. So you see, we have all these things we know, and Lagrangian mechanics gives a place to all of it, you know? Like, one of the things that's problem with Newtonian mechanics, all these things just come out like separate pieces that you got to remember. And here, there's just a beautiful place for it all, right? You can also see that with this definition, mass doesn't, this mass in this way defined, you know, there are many ways to define mass, also a rest mass, that you say this can only be done at V is 0, and you would have the rest mass. And I'm just allowing any output, huh? Okay. But you see, it all has a nice place. So this could be now a function of V if you define it this way, right? Okay. All is brought together. And my attempt with this, this slide here is to show you how it also brings together things in economics that are just lying around there and possibly can be cleaned up. I'm not saying we're going to correct them. I am saying that sometimes you have to make small adjustments to what the terminology they're using or how they're writing it down to get it to be aligned in the way we think about it. And if it's in spirit the same thing, then that's fine. Okay? All right. Now let me go a few more steps. So the potential energy, those are what we've been calling the benefits of ownership, right? So you can, typically it's known as the cost of storage. You know, there's a theory of storage, huh? And then this whole thing is just the cost of having the storage, a negative, right? Now we subtract this. This is a benefit. We put the minus sign there. And then the convenience, it would be the marginal cost of storage. That thing exists too. They call it the marginal storage cost for some reason. There they use the adjective and there they don't. I guess I'm a native speaker, so storage cost sounds clumsy, but marginal storage costs sound good. Huh? I don't know why. You have to get an English major to explain that. All right? So enough said. This is just kind of the foundation. Of course, the firm is a very complicated mechanism with all kinds of things, but underlying it somewhere must be an I element, right? Because it's selling things for a price. Now, the minimum you'll have is this part in Lagrangian. Most likely, it also has some inventories, you know, so it will have this. Now, let me make one more remark about this. Like economists, they distinguish often between two types of goods. They call them durable and non-durable, or consumer goods and capital goods, or commodities and real capital, property, plant, and equipment, things like that. Okay, so they make a dichotomy between two types of goods. Whether this is a house, which they would consider durable, or whether these are apples or chocolate bars, which they consider non-durable, consumer goods. All right? Huh? Consumption goods. Now, what's the difference is that usually these consumer goods, all you do is you don't really store them, at least an economist doesn't. You just kind of, it's just an I element. They just sell it or buy it, you know? And you can find that back in your supply and demand graph where you see there's nothing else the matter. Then there's the other type of goods. If you look at the theory of the firm, that's all the equipment they have. And that they assume you just have and it just stays there and it doesn't get more or less while they're doing this analysis. So that thing would only have potential energy, all right? Because you just somehow stored this. So they break it up. They usually don't consider both at the same time. So they won't consider commodities to be simultaneously stored by the firm, or if they do, that this number is unimportant, okay? So they never look at these inventories and things like that. On the other hand, when they have capital, they'll say, well, the theory of investment is different than the theory of production. So they'll assume the capital goods remain. Now, they also will say that there are two types of analysis, the short run and the long run. Typically, the short run, they only look at the kinetic energy, and the long run, they will only look at this potential energy. All right? So in long run, your capital goods can change. You can retool your factory. You can do all kinds of stuff. But in the short run, their analysis is different. Okay? So be aware of that. We are making a unification not only between buyers and sellers, or demanders and suppliers, but also between storage on the one hand and buying and selling on the other hand, right? For capital goods, when you buy and sell them, you call it investment, right? If you have just regular goods, when you store them, you call that inventory, right? So they all have different names, but either way, your Lagrangian is just going to depend in general on both of them, you know, but you just ignore the one or the other depending, all right? Yeah? So this is a little bit different also. I mean, that's why economics is so complicated, right? It's got 20,000 theories and everything is just running around each other. And that's one of the great things of this using mechanics. It all hangs together, so you just need this one theory. Or bust, right? If you have to add theories, you should stop, all right, for your thesis too. Just do it within mechanics or nothing. Otherwise, you're. Oh yeah, and I put this in there. Now, one of the other advantages that we mentioned last week of the Lagrangian approach is that you don't really need to only look at systems that have only 2 dimensions or 3 dimensions like Newton did, right? So you can look at weird submanifolds, and then the particle just moves on there, right? So you can look at these rotating systems or anything. And the picture you have in mechanics is that this is called a constraint. So the particle will be constrained on this thing. And effectively, what happens is there are some forces that are infinitely big, right? That keep it on there. And if you have a constraint like this, where it's just on a submanifold space, this is also called a holonomic constraint. You may have encountered that term in some of your classes. Is that true or not? Has anybody heard of this thing called holonomic constraint? Yeah. And so you can have some kind of bob on a wire, and it's just sort of a rod and it's turning, and it can't go further, so it's constrained by the wire to stay on this thing, right? Huh?
Yeah, Max,
yeah?
Both the quantity of guns produced and the quantity of butter produced, they're both Q dots, right? They're not Q's.
Yeah.
So isn't the definition of a holonomic constraint that it only depends on the generalized position?
Yes. So this is a bad example. This is a bad example. Yeah. Yeah, so this is a non-holonomic constraint. Huh?
Yeah, exactly.
Yeah, this is a very bad example. Now, when I looked at it, they also said this works for capital goods, but yeah, this is a bad example. Thank you.
what I think, for example, in a holonomic constraint, you could have limited storage, for example. So you can only have like certain combinations of guns and what is the other thing, resources in your that fits in your storage space, for example, and that would give you a holonomic constraint.
That's right. So very typical. You can have only 100 apples or 100 pears or 50 apples, 50 pears in your storage room. And this has no, it's like a spring with, normally a storage will be a spring.
It's like the problem if it.
Oh yeah?
You have to limit it. Limited buffers.
I see. So one way to look at this is that it's a spring with infinite stiffness, right? So that the forces keeping this thing there are infinitely big. This is normally the way you should look at it. So I think Emil is giving me the right example, and I thought of that, but for some reason I lost my bearings this morning, and I put in the wrong example. This is no good. And I remember having a conversation with Emil saying that this was not it, and now I did the mistake again. So after having told him that, discussed with him a while ago that this is the wrong example. But that's right, so forget about this. Just forget about this slide. Huh? So what you can do is you have some limited storage, you have two goods, say apples and pears, and you can either use the storage entirely for apples or for pears, or if the things go, you know, about equally big, you can have this this type of constraint, right? Huh? And normally you would have a spring, you know, to do that, to get them, you know, connected. But you can make the spring infinitely stiff. So that really means that if the system was to go off here, there's an infinitely big force holding it on. Huh? And that thing is called the constraint force, and that's how you can measure it. Now, if that force is not infinitely big, then of course it can go off, but then it's better to think of this as your storage capacity, add that as a variable, and then go into some three-dimensional space where you have a two-dimensional submanifold, I guess. Huh? So you can play all these tricks. Now, whatever you do, don't make the same mistake I made. Huh? This is wrong. Okay, thank you, Emil. Any questions about this correction that I just added to myself? I guess what I wanted to say is don't get too stuck on the idea that this is only applicable for Newtonian mechanics just because I plugged this in and this in as examples. These definitions are all perfectly valid, and you say they don't depend on this L, right? Huh? Okay. All right, now here is the, here I want to just sketch out how this whole thing will work for consumer theory. So firms and consumers, they're considered differently. We want to do them the same. Now, consumer theory is also a very complicated theory, and what I want to do here is just take some of the major concepts and tell you how it might fit in here. All right, there's a lot of discussion here possible, but this is how I think about it and how you could also think about it. So the first, remember how the first thing we want to do is that a consumer could be minimizing cost, but that's really not what he is doing. He is interested in utility. Huh? And how does he interest in utility? Now, the way this is set up is actually very pretty. What they do is they give a consumer some alternatives. What do you prefer, an apple or a pear, right? And if you prefer an apple over a pear, you write something like this. An apple is preferred over a pear. And then you can prefer a pear over an orange, right? And from this would follow that you prefer apples over oranges by something like transitivity, right? And you can set up a few rules of this type of preference behavior. Now, what would you do? So if you do your what-if scenario analysis, what you would be doing is, okay, what do I prefer? Do I prefer Bach over Beethoven, or do I prefer Beethoven, Brahms? No, this. So I'll do a little bit of that and such. So all these variations that you're doing, you know, they can think of that as being variations on how much happiness you're going to derive using this kind of preference ordering. So you imagine these preferences to be things you want to change. And as soon as you prefer one option over another, you can wiggle it a little bit. Huh? Now you can say, well, why would I wiggle it? Well, this is a tradition going back also really far to the Enlightenment, that there were philosophers who, at a certain point, saying, well, why do human beings do anything at all, right? And they're saying their idea was there must be something called their happiness, or something that they are trying to increase, their well-being, you know, their good feelings, whatever, and something else like pain they're trying to avoid. So what they try to do is to say, well, is there some kind of number that we can associate with this guy's well-being that he will be maximizing? And ultimately, people decided on this word called a utility. So it's unclear what it exactly means, but the idea is that there is some kind of concept, whether it's happiness or satisfaction or good feelings or kudos or whatever you want to call it, that we're maximizing and we can like assign a value to. This is the basic underlying thing. So what would we be maximizing? Well, we'd be minimizing S, so we will try to somehow maximize the negative of S, right? The benefits. This is what we've been calling the benefits. All right? And how do we do that? By asking ourselves these questions about what we prefer. Do we prefer this over that and prefer that over that? And the idea is only when you're indifferent between two options. So if you have so many apples that you become indifferent between that and pears, then you are at the right place, right? So indifference is then the test they use. It's a big theory. We can give enormous amount of lectures over this. And when you take advanced courses in economics, they will look at consumer theory as based on these preference ordering. And it's a lot of mathematics trying to derive functions from that. We need not go into this. What I want to say is that this concept of utility and preference ordering is very similar to how action maximization would go, right? So whereas a company may do a what-if scenario, how to minimize total cost, a person, individual, he or she may just wiggle, like have different ideas. Okay, what do I want to listen to? What kind of music? What apples? Do I want? Instead of the grocery store or looking at these apples and pears, and then they said, I want this and this. You know, in the mind, you're quickly going through all these variations. All right. Now, if you latch on to this idea, then it gets a little tricky on how they define things. But the consensus, there are many types of utility functions, but the consensus appeared to be that the negative of Lagrangian is what's called a utility function. There are many forms of utility. You have 6 or 7 different ones, and you have utility under uncertainty and von Neumann more. But this is what would be called in consumer choice utility function. I like the idea of function again, because this is indeed a function. This would be the total utility you would acquire over the period, but it's not a function, right? So it's some utility structure or something. The thing that's not good about this, you're not going to maximize this. You're going to try to maximize minus S, okay? But nevertheless, this is then called a utility function. All right? So for the consumer, the problem is actually even more obvious, of their solution is a little bit more obvious, that this calculus of variation, that's the business of arranging your preferences so they become to some kind of indifference level. And you can do this whole thing by seeing your total lifetime utility. They talk sometimes about the lifetime utility that you maximize. This is the intertemporal, right? Yeah, this they sometimes call the intertemporal. Inter means, so this thing, if you integrate it, you'll see that this thing is at the current time, you have to look at this one. So temporal will be that whole lifetime, and the inter means all these different points between T1 and T2. Huh? Sometimes called the intertemporal utility. But if they just say utility function in this context, they typically mean this. There are other writers who mean something else. If you look at von Neumann and Savage, they would look at this thing and call this the lifetime utility. But it's not a function. It's like a whatever. Let's not get into it. But this is one solution to this. And this is a solution we'll be adopting. Okay? So the negative of your Lagrangian, you could think of it as a utility function, or just, the benefit, of course, since it's the negative of the cost, the total benefits. The nice thing about the word cost and benefit, it emphasizes the units which are in, in currency. Utility, you have something called a money metric utility, but it's not so clear whether it is really measured in dollars. Huh? Now, if we think of this intertemporal utility, or this utility function, it's made out of two parts, right? I just put a negative sign in front of it. So the total running utility consists out of this that is due to your buying and selling, and this to what you have in storage. So that's interesting, right? So you can make yourself happier, it says, either by going on consuming a lot or buying a lot, or just having a lot of things. Lekkere hebben dingetjes, as we would say in Dutch. Huh? Huh? Now, I think, and this is something that I like to think, I'm not convinced every economist thinks of this, but they make a big difference between different types of value that you could ascribe to something. And I'm using now the word value as the same thing, meaning as a theory of value, not in the Laplace transform, which is a way of valuing things with a utility number, all right? And one important distinction that's made, and that I want to map onto this, is there is something, the use value and the scarcity value. And this was first pointed out most poignantly by Adam Smith. So Adam Smith came with this paradox, this very famous paradox called the diamond water paradox. So diamonds are totally useless, right? And I'm saying useless in a good way, in the right way here. I mean, what are you going to do? Can you eat it? Can you heat yourself with that? Water is extremely useful. If you don't have any water, you're dead, right? If you don't have any diamonds, you can live quite happily, right? And then, so why are diamonds so expensive and water so cheap? And the answer he gave is the only reason is because diamonds are scarce. There's very few of them in the world. These diamond mines are very limited, and what is there is being even further limited by De Beers and company. Huh? And there's just very few of them to be found, and you can't really make them because the pressures needed are way too high. Huh? So it is carbon, but so it's very scarce. Huh? Like gold is scarce. As soon as it's abundant, then it loses its value. So the reason that they have so much value is because of the scarcity value. Water is everywhere, you know, especially here in the Netherlands, you know. We are drowning in the water, huh? So, of course, when water is scarce, like it may be in the Sahara Desert, it can become quite valuable, and you most likely will be willing to hand over a few diamonds for a little bit of water at that point, okay? But water has a very big use value, so this splitting up of your total, the total utility into these two components, I mean, I'm not saying this is the right way to do it. There's all kinds of other ways, but it's nice to think that since the potential energy is associated with scarcity anyway, right? And this is how we allocate scarce resources based on the convenience that holding them has, you know, and that's definitely the feeling you have with a diamond. It's just, you know, bling, bling, right? Huh? And lugging around a bottle of water. I mean, it's a little bit of water, enough to drink is okay, but it just doesn't look so good in the opera, you know, or at the party. So this is a nice distinction to make. So this is what I like to do. So is make this thing of use value, or the value. Sometimes they would say the value it has in exchange, but usually they think about that as a market price rather than my own price at which I'm willing to exchange it. You know, that you can also think of this. Huh? That's a nice way to think of it. Okay? Then you can look at price. Well, it's just negative of the marginal utility then, you know, which is a very common way economists will do it. Except here, this utility is measured in dollars. Otherwise, they may have to look at a ratio of prices because their scale, they want to get their scaling to come out. Huh? And then mass being positive is a very famous law, the law of diminishing marginal utility. Like the more you have of something, the less your the added utility to you is of getting it. All right? Now, what is the potential force? I have to say it's very hard to find anything because it's so rare for economists to deal with stock variables. And if they deal with that, they just mix and match it. So they will just have this attitude that we also had in the theory of the firm, that you can do everything either with a flow variable or a stock variable. You say in the beginning what it is you're using, and then the theory is all the same. So you can just say P is minus dl dq, if you just decide that now we're looking at a stock variable, right? So, and then they will just call this the price. Although we would say that's not the same. That's, you know, that's a force. You can't do that. The units are not right. But they are very liberal with this use of price. And of course, the first economic engineer that Emil was presenting, he is slightly less liberal in that he kind of gives us the units of this thing in advance, but then afterwards, conceptually, I think it's fair to say that he seems to jump up and down, right? Huh? Would you say so, Emil? Huh?
Yeah, it definitely makes a mistake. Sort of, because he considers it over an entire year, he sort of forgets about the whole time dependence, which only, in that sense, you can only do a partial equilibrium because if nothing's changing anyway, so then you can, and the Q's and the Q dots don't really make a difference anymore. Yeah. Also because it doesn't consider the potential anymore. It doesn't really matter whether you consider it to be a Q or a Q dot. Yeah, but when I was reading him, I noticed that sometimes he'll be talking as if he's increasing his stock, but then he's forgot that he has none, right? Huh? And the other thing he does, which is interesting, he starts off with saying that all that matters is your desire, right? Huh?
he never really defines it very well, but he says that that's the thing that's going to determine your utilities, okay? That's in the very, very beginning of his thesis. A very interesting thesis, actually. And what I like to do is his notion of desire, which is the same as a want. We could think of this as a force. So his statement interpreted is that his statement that everything is decided by human desires is to say that all of this in the end comes down to a bunch of forces, although I like to see it in the other way around from the Lagrangian analysis. All right? So this is a way I've kind of filtered in. Huh? And then when they go through all of that, they will, you know, they have something called the Equi-marginal principle. So this marginalism is really, it's also a very important step in economics. And there was always this problem also with how do you compare things? Like why does my utility for apples change? If I have more apples, and how do I compare these apples with pears then? Till somebody finally figured out, and it was a kind of a joint effort, that it was not the total utility that mattered so much, but the marginal utility. How much do you get extra for, how much utility do you get extra for buying an additional apple? And you can compare that with how much you get extra for buying an additional pear, and that comparison is important, not so much the total number of pears or the total number of apples you have for buying, okay? So this was a big breakthrough, and it was called the marginal revolution. In fact, that YouTube series that we always recommend is from Marginal Revolution University, right? So this idea of marginalism, that we're always looking at partial derivatives of the utility function, is central to economics. Comes from this idea of marginalism. And all of neoclassical economics is built on this concept of comparing marginal utility, okay? Now compare that to this. Both price and force are marginal utilities. The one with respect to your consumption, right, your demand, and the other with respect to your, how much you have in stock. And those you have to compare. Now what the Euler-Lagrange equation does for you is tell you exactly how you can compare them. Now this is, again, a complicated equation. This is just not saying that every one little p dot for one thing should be equal to the f. No, this could be in big matrices with vectors and everything influencing everything, and this change in this momentum influencing that thing. So it's a whole bunch of system, but whatever it is, all the ingredients are marginal utility, okay? And when these marginal utilities are equal, right, then you have an equilibrium. This is what happens, and this is called the equi-marginal principle. So it's a foundation for neoclassical economics. And I think it's very pretty how the Lagrangian setup that actually defines these things as marginal utilities gives us the generalized Euler-Lagrange equation that just says, well, everything is about comparing these marginal utilities. And by the way, this is exactly what the law of demand is, because that extra step is not being made, okay? That although economists do this, the theory of demand as laid out with demand and supply graph is seen separate from that. And it's not really derived in a quantitative manner. Of course, they say, well, it follows the law of diminishing marginal utility, but the fact that you can derive the Euler-Lagrange equations and that those are the same as a sort of generalized demand equation, that concept is not there. All right? So this slide is really there to convince you just how natural the yeah, the Lagrangian approaches. It may seem very difficult, but when you look at it, basically, the big ideas of economics, equimarginal principle, marginal revolution, scarcity, utility, right? The law of diminishing marginal terms, and the basis in preference, it's all there, right? Well, I think that's very pretty, and that makes this approach so attractive, you know? Because if you just started off with our Newtonian approach, where would all these things fit in, you know? Like, what do you do with preference? What do you do with all this? Where are the utility functions? Huh? And here, yeah, you can dispute it, but it does ground everything in a very big, nice picture. All right? Now, ordinarily, I would call now a break. But this lecture is going to be a little bit shorter. We're going to break. We're going to stop it at 3:30 approximately because there is the DCSC pub quiz. So what I want to do is test your forbearance and go an additional half hour. All right? Huh? Don't worry, after this lecture, you'll all be able to go on a Christmas break and you'll be able to recover from this onslaught of...
we have Thursday.
Oh, we have Thursday, yeah, but lecture-wise, you'll have a few weeks to recover from the onslaught. All right? This stuff is just really nice, you know. You should just be able to enjoy this. I mean, some of this you won't really need too well in your research. You can just do it with bond graphs, but it's really important for you to. All this stuff is just flying around, and it's really nice to get it all at the end of this course, all put together. I go, okay, you know, huh? This is where it all belongs. Very pretty, and I hope you guys agree with me. Oh yeah, what I want to now do is look at fixed cost. So the cost all depend on something. You know, the use value of it depends on how much you're buying, and the scarcity value depends on how much you have, right? But companies and also individuals, they have something called a fixed cost. It doesn't depend on anything. You know, even a company if it's not selling anything, and you and I, even if we're not buying anything or don't have anything, we're just going to make some fixed things. Right? How does the theory treat that? Now, the Lagrangian theory actually is a very nice way of dealing with that. And it's also a central issue in physics. And in physics, it's called gauge invariance. And that's a fancy word, but you can kind of see a gauge is a measuring device. So it says that you can measure these costs away from like a fixed cost kind of thing. Okay? So I quickly wanted to point that out to you because a lot of students, they have these fixed costs and they add them to the Lagrangian, but they don't know if it really can do. All right, here I just want to show you that you can do this and that it's just not a hack, but it's something that's done in physics as well. So consider the following. You have some fixed cost kappa, just in, you know, currency per year. And I'm going to just add that like a typical engineer. I'm just going to add it to the Lagrangian and see how this thing works out. So now my total period cost or utility or whatever is the old one plus the fixed cost times the difference between the end time minus start time. That's just the time interval, right? Obviously, right? In dollars, okay? Now let's see what happens when we minimize this. Now when you minimize this guy, it's the same thing. Cut and paste, it didn't go wasn't quite finished. It's the same as minimizing the one where you just integrate this out, all right? Huh? So the minimization, you get the same answer independent of if you plug in anything here. Now, why is this the case? Well, it's actually super easy to see because why is this so easy to see? Yes, exactly. Yeah. Yeah. That's right. Yes. So it's not going to change. So if you do any variation, I mean, nothing is going to happen here, right? Huh? So that's right. So you can vary this thing the way you want. You know, if you look at this thing, this variation is going to be 0, right? So there's no variation. So this one just disappears. Now it turns out, so you could just add fixed cost and you can just subtract them and to get everything at 0. So notice that takes care of a lot of those shifts you guys have, you know, where you put in a flow source, I don't know what, you can just leave them out. Huh? You get the same result. By the way, I wanted to point out here, you see with this definition, you also get that nice downward sloping stuff for free and everything. It's just a question of looking at utility rather than cost. You know, why this price now has to be a negative number, that's all. Huh? And here you see that this thing, yeah, it's not going to make a difference on the minimization. And in fact, it's very easy to prove, and I'll leave it to you to look at that, but it's a standard result that this thing doesn't even have to be a constant. It can be any total derivative with respect to time. And then you will just add this is sometimes called a bequest. So this will be an inheritance, right? And this will be a bequest. And makes no difference. So what happens at these endpoints is not part of the optimization you're doing. Of course, if this is not a total differential, this integration can't be done when you're integrating this Lagrangian. The point is you can just do the integration here. You don't, huh? And then you're in trouble. So a lot of stuff, anything that you can express as a derivative, really a time derivative, a total time derivative, is going to be fine. So fixed costs you can just throw in there. Right? So typically you will have some graph like this, and then here are the fixed costs, and then they add this, and this thing you can just throw it out. You can just move this down, and the Euler-Lagrange equation will give you the same thing. Notice the power of this Lagrangian method. How long will it take us to prove all this with Newtonian mechanics? We're sitting messing with reference frames, and then this, and we got to imagine that, and such, and so. Here you just plug it in the optimization, you find out you get the same Euler-Lagrange equation as in the other case, you go, okay, done. Huh? You know, and seriously, if you think about it, you have some fixed cost, and you're deciding what course to actually take. How can it depend on your fixed cost? I mean, they're fixed anyway, right? Huh? All right? So when you look at different costs that you may have or forces that you may consider, usually costs that you have, check whether they can be thought of in this way, and then you can just like subtract them and leave them out of the analysis. All right? This makes a lot of thinking easier. Okay?
Dynamics, I totally see.
Yeah.
It clears it up.
Yep.
But sometimes you need it, right?
Yeah.
For example, airplane, yeah, flies up at 1,000 feet high or at ground level. The dynamics are the same, but it really depends on you want to crash or do you want to.
No, I understand that. And it's the same in economics. If this is a bequest and this is an inheritance, people with a big inheritance, this makes a big difference. You know? No, I agree. Huh? But when you make your model, you're typically interested in the dynamics. So you just leave it out, and in the end, you add it all back in if you want. Right? Huh? That's the message, really. Huh?
Yeah, okay, so yeah.
Yeah? So you don't have to like carry it along in all your analysis and this and that. You just say, all right, I'll leave it out, do your optimization, you have your dynamics, and then when you have your results, you boom, you put it back in. You say, oh yeah, I also got this big inheritance, or I have this fixed cost. Let me just add it in. Huh? Yeah, but don't worry, a bond graph, what's going on, you don't really care, right? Huh?
The bond graph already does it for you.
Yeah.
You don't have to.
Yeah, the bond graph already does it for you. Yeah. No, that's right. So it's a powerful result, and you can use this to check what stuff you can kind of, get out, to simplify it. All right? It's really very pretty, you know, all this stuff is really very pretty. I mean, the ease with which you see things and do things is just, it's almost too easy. That's why it's so hard, you know? It's almost too easy. It's almost too obvious. I always find it hard when it's too easy. I want to do 2 more topics and 1 more example. So I guess I can do this in there. So when we did Newtonian analysis, we had this thing called partial equilibrium, right? So that was Newton's first law, and this is also called Marshallian equilibrium. So this is the old idea of equilibrium. So prices are constant, and this is some constant price here, okay? And that's the condition of partial. This is the same as a free particle, right? In mechanics. It's just kind of moving along at constant momentum, and there's no forces acting. Now, Newton's law actually lays down that there must be such things as free particles. So what Newton said was, okay, you have this space going on, right? And for us, these are commodities. And it must be that the space is such that you can imagine that if it's here, it's going with this velocity. If it's here, it's going with that velocity. It will just kind of maintain this velocity. This must be possible to imagine, okay? Now, how do you translate? And this is what is later called the homogeneity of space. So it must be possible to imagine a space that is homogeneous, namely that I can take everything and just kind of shift it over, right, and nothing will change. So if I have some experiment of physics that I'm doing here, or I have this thing, I could carry my whole apparatus to the room next door and run the same experiment, but that room is not going to be any different than this room in terms of space itself, right? Of course, it could be if somebody has a magnet there and starts pulling it, but those are extra elements in that room. If I just subtract that all away, I must be left with some space where this distinction does not exist, all right? Okay? So one way to say that is that space, without any springs or other things, you know, the Lagrangian cannot depend on the stock, right, on the position. And what we are saying is in order to do economics, it must be possible to imagine that there is a situation where you have no storage. You just, everything you get is just from acquiring things. And that's basically what Marshall assumed when he was doing this. There, you know, this graph doesn't have a Q. It only has a V and a price. Right? So he's imagining the existence of this thing, okay? So if we're doing Lagrangian mechanics, our requirement will be that it must be imaginable that you don't derive any convenience out of stuff. So you don't care. You can imagine a world where you have just enough water all the time. You're not going to care about holding a bucket with you, right? Or just whatever, independent of how much you've consumed. This is unrealistic, but you imagine it, okay? That thing is an inertial reference frame. Now, this will be the assumption translated, Newton's assumption translated into the Lagrangian method. It just means that the cost cannot depend on the storage. That's all this means, right? Okay, so if I change the location, that's this dq, then my cost can't change, right? It's independent of how much I have. Now, if I plug that into the Euler-Lagrange equation, I find out that price must be constant, whatever it is, okay? And price constant is precisely what partial equilibrium demands, okay? That the existence of this thing, all right? So it's actually a very pretty picture of what it means to be in free motion, or what it means to be in partial equilibrium. It just means that for you, this commodity space is a homogeneous space. you don't care where you are in that space. So you're in your edge of box, but you don't really care whether you've consumed millions of gallons of water or 1 gallon, or you don't really care. You don't keep track of it, right? Huh? So it's a very pretty picture. All right? So this idea of space being this amorphous, not different at different places, that you could do economics at one set of commodities and the same law of demand will apply with somebody with a total different set of holdings is very powerful. It's the same powerful idea as a physicist can do an experiment involving velocity in one room as well as he can do it in another room and expect the same outcome. He can use the same Newton's law, right? And we can use the same law of demand, okay? But you see now how this idea is so neatly stated in terms of homogeneity of space. Now, Emil does some nice work in saying you can also see space, the Lagrangian, as being invariant under some kind of group where you shift this thing, and those are called Noether symmetries. But it basically captures the same thing. You know, whether you're looking at what things you can do to the thing that won't change the problem, or what I just saying, well, how does space look? And, you know, it's all the same, right? Huh? Also called a Noether symmetry. Okay? So this is sometimes said that momentum is the invariance to a shift. You know, that gives the notion of momentum meaning. That's why we have it, right? That's why we have it. That's why it's a useful thing. Okay? So the invariance with respect to translations in space. So price is useful because we can imagine a situation where we're invariant to how much stock we have. Now, as momentum is related to the symmetries of space, energy is related to the symmetry of time. And this is kind of an interesting thing that keeps them both separate, you know? So what you want to do with a physical experiment, you want to be able to do it at an arbitrary location here in Delft or in Boston, or you don't care. But you also don't want that tomorrow that experiment is going to give you different results. So you want that same kind of homogeneity in time, so your laws don't change with when you perform the experiment or where you perform the experiment. So what you really want is to imagine a time that is, at least in principle, homogeneous. And in that time that is homogeneous, you start doing those experiments and quantifying a law. And as you get conservation of momentum, or the invariance of price, when you look at the symmetries of space, you can look at the symmetries of time, homogeneity of time, and you'll get this the conservation of energy or income or surplus, all right? Total surplus, or economic rent, I would say. Huh? So this will be the conservation of rent, economic rent. Huh? So we have the same condition. Our cost can now not depend on what time is, and from it will follow this. Now this is a little harder to see, but nevertheless, it's there's a simple derivation, and I find this thing always kind of magical, you know. And we'll come back to this when we do Hamiltonian mechanics, because then we don't have to do these little tricks. We can just immediately write down Legendre transforms, and this will become even more obvious maybe, or more fundamental, not more obvious. But now look at how your Lagrangian may change in total over time, right? Huh? Now I can, you know, this Lagrangian is now dependent on Q and V, and I already built in that it didn't depend on time. So in this one it is, but you have to assume that it may. So let's put that t back in there, right? Huh? And then if I look at the total derivative, well, I just chain rule my way through there. So I first do a derivative of v times v dot, and then I look at this thing, right? So this will be the price. Now look at this thing, this will be the convenience. And then I have this guy here, how it changes with time times t dot. This is 1, right? Now if I plug that in, I get this. If I plug that in, and I know that this is equal to P dot, so I can plug that in. And this becomes 0 because this thing is by assumption 0. So I find that this derivative is actually equal to, if I multiply P by V, and if I take the derivative, that's what I get, okay? Huh? This is interesting. So what is P times V? Well, this was our connected co-energy, but this is P V, so that's this whole area. So apparently, the change in this whole area is the total change in my cost. I find this somewhat magical. I've never been able to fully comprehend why this works. I've always seen it, but that the total derivative of the cost will be equal to the derivative of, this is what sometimes we call the revenue.
I never fully understand what the difference is between the total time derivative and the partial time derivative.
Yeah, so this is the difference, right? So here you are.
Yeah, but
Yeah, no, I'll help you. So what is the total derivative? You let everything vary, right? So what is this partial derivative? I have to keep Q and T constant, right? So the trick is, you see, this may be a function of Q, V, and T, right? But Q can be a function of T, and V can be a function of T, and T could even be a function of Q if you wanted to, right? So what I do with a partial derivative, I keep this one constant. If I do a total derivative, all three are changing. All right? You follow that? So here I say I'm only going to vary this guy, right? And these two I'm going to hold constant. That's what I say here, right?
What is then the partial time derivative?
Well, I keep Q and V constant. I mean, it's ridiculous because you think to yourself, how can I keep Q constant if I change time, right? But that you got to imagine that something can just change only because it took a little longer to do so. So it singles out the one effect that comes from time alone, not induced by a change of position that also did it, right? So this is the direct effect.
Physical example, partial difference.
Energy that you put in the system. So you have a conserved system, right? So
the input.
That will be an example, yeah. It only depends on time. It can't depend on the position and the velocity, right? So you keep position and velocity constant, and I just throw some stuff in really quick because otherwise everything starts changing. But this is a partial derivative, so I'm doing it really quick. Very small amount of time. All right? Okay? But what is momentum? Momentum is the partial derivative when I keep the stalk constant. Now you can say, how can I increase the flow and keep the stalk constant? As soon as I have a flow, my stalk is going to increase. But you have to imagine that it goes a little change so that the stalk stays constant. Okay? That's what this exercise is. All right? So the total effect is the sum of all three, right? When you keep the other two constant, right?
All the other partials, that's some kind of intuition. The partial derivative to time, how it differs from the total derivative, the total time derivative. That they didn't really seek it.
Now it does, right? Yeah. So just imagine this thing moving at a particular speed, and it's got some potential energy or it pulls a spring, and now you just throw some energy in there. Here, chip, right? Okay. You can ask yourself how, but for instance, friction does this. Friction will change this thing over time. It won't depend on anything else. We'll see this later in this course. And actually, it's a little bit tricky because time gets used here a little bit too much. One's for parameterizing the path and the other for taking these derivatives. But Don't worry too much about that right now. We'll sort all this out when we do friction in the Lagrangian context, okay? Huh? But anyway, if I do this, if I know this result, then I can just bring this to the left side, right? And then bring the time derivative out, and then I'll just get this as 0, right? So this is sometimes called the revenue. So that's just the price times the amount. That's not saying the cost, because some of it you bought at a lower price. But at this point of time, this price, that's your total revenue, right? These are your costs. And this whole thing together is the revenue minus the cost, and it's here called, with the kinetic energy, the surplus. If you then add in the benefits, then it's called the total economic rent, okay? And that thing is constant. So if you don't pour in rent, economic rent, the total economic rent will stay constant, okay? And it will distribute itself out over your I element and your C element, over the demander and over the holder, all right? But it can't get it out of nowhere, right? And that thing, that economic rent, cannot come out of nowhere. That's called the conservation of energy, or the conservation of economic rent is what I call it, right? But it's really saying that as long as you don't like just pour stuff in or take some stuff out through damping or other things, if you just localize yourself to this demander, this I element, and this holder, this C element, then the surplus has to go somewhere, right? Either you put it in your storage as a benefit to be sold later, or you sell it now and you cash in on it, right? And you can just prove that. And this means that if you don't have a process that only depends on time, so it's irrespective of time, that you can do your experiment at a later date. But you've got to have an isolated system. You've got to isolate it from these influences from outside. So this damper takes energy out and gives it to the environment, right? So you lose it. Okay? If you have a source flow, a flow source, or an effort source, I'm starting to talk like you guys, then also it comes from the outside. So if you repeat your experiment a day later, if that source has been acting, you're not going to get the same results. You got to isolate it, all right? And then, you know, that this isolation means that this is 0, and it means, So what we need to do conceptually is imagine that time is such a thing that we're able to conceptually isolate things so that the change of it solely due to time, not due to the other variables, is 0, right? Okay? And that change is often the work, this is what we call the work done on it and things like that, all right? So that's how we chose time. So you see the idea of energy came out of this idea of what time is and how we use it, okay? So the homogeneity of time implies there is something called energy that's conserved. The homogeneity of commodity space, or just regular Cartesian space outside Earth, implies that there is price or momentum, and that can be conserved. And we have the two great conservation laws tied into two important ways of measuring: the stock and time, or in mechanics, position and time, right? Very pretty, okay? Otherwise, these laws just come out of thin air. But energy belongs to time in the same way that momentum belongs to space. Without space, there's no momentum. Without time, there's no energy. All right? And the symmetries of time and momentum imply the existence of momentum and energy. And similarly, in economic engineering, the symmetries imply these concepts. Okay? So this is my take-home message. Just get everything in. I had one more slide. I'll go through it really quickly just to tell you what it is, and then you can pause and ponder, as some people on the internet say, over this. But you can also look at, you see, in physics, you can take some device and turn it, and you can do the experiment. It's going to be the same as long as there's no gravity, so I got to do it like this. And you can do the same in economic engineering. We've done it for credit, right? So these things you can turn, they're the same. We talked about credit. You can define interest rates in Lagrangian. This price is now the amount of credit. The velocity is the interest rate. And if there's no convenience to retaining the interest, if you just want to, I don't care how much interest I have, that's past tense. That's what you typically do on the stock markets. Whatever I've received, I'm not going to look at it. I'm only going to look forward. Then you can derive something called that the credit that you have outstanding or the financial capital is a constant then, you know? And this is the conservation of angular momentum. And it comes from the fact that you can rotate things around either hyperbolically or along this line or along here. And that things are the same. All right? So in physics, it just means if you have some apparatus and you take your table and you turn it 30 degrees, nothing is going to change. All right? But you got to build that in, right? And atoms have it built in, you know, they're spinning around like that and all this stuff. And we can build it in by thinking about either compound interest, simple interest, or the circular interest, okay? Revolving interest or something, or whatever you want to call it. Okay? So those are the three great conservation laws. The law of conservation of linear momentum, the law of conservation of angular momentum, and the law of conservation of energy, all derived from this Lagrangian method and all associated with symmetries in either time, in space-time, okay? The picture is very pretty. And the second thing, the other thing, part of the lecture was about the different terminology that you may use depending on whether you're looking at utility or cost, okay, in how you would treat constant cost and other bequests and things like that. So with this, I want to round off the Lagrangian analysis. Thursday we'll meet once more with student presentations, and then after the break, we'll continue with the real pretty part, which is Hamiltonian mechanics. If this were not pretty enough, right? It's really beautiful, I think. Okay? See you Thursday.